All right, so before we get into the actual problem, what I wanted to do is bring it back to the refrigeration cycle, because that's ultimately what the problem is centered around. We're going to be doing a lot of other calculations, a lot of other math to kind of build up to get the information that we need for the cycle. But I want you to understand kind of my logic instead of just diving right into the problem. Let's come back to our cycle and figure out what information might we need. Okay? So what I've drawn here, I've just drawn the PFD out. I've labeled the states like we did before, listed out the pressure, temperature, entropy, and enthalpy. And let's go ahead and apply our simplifying assumptions. So remember, across from 1 to 2, what did we say? That pressure 1 is equal to pressure 2. Remember, because we assume that we're still at vapor-liquid equilibrium, remember we have up here, we have vapor plus liquid. And again, we have isobaric cooling. We come all the way to saturated vapor. Remember, that also means that T1 equals T2. Now, from going from state 2 to state 3, remember we went from a saturated vapor to a superheated vapor. And recall that we made a simplifying assumption about the compressor. Remember, it was an ideal compressor. It was reversible, i.e., the entropy at state 3 is going to be equal to the entropy at state 2. So the work that we're inputting is reversible work. Remember, from our assumptions, not going to be true in real life, but our model we're trying to build here to get the best case scenario. Remember the other assumption from 3 to 4? What did we say here? We have isobaric heating. Or excuse me, isobaric, taking it from the hot side. It's actually cooling the system, but it's going to be isobaric here, which means that pressure 4 is equal to pressure 3. Now, you see, I made this note the last time, but the temperature 3 is not necessarily equal to temperature 4 because we go from superheated vapor to saturated liquid. So we don't really know, we can't conclude there that the temperatures will be the same. And they're not going to be the same. Now we've applied all of our assumptions here. Can we solve? I guess the question there is, solve for what? Well, in our problem statement, what were we doing? We were trying to make a new product. Remember, the new product is going to make more money for us. However, this compressor is going to cost us money. Nothing else in this cycle on a regular basis is going to cost us money. This is what's going to generate a utility cost for the electricity to drive this compressor. So do we have enough information to solve for the work of the compressor? The answer is no. There's some other things that we need. And there's a plethora of ways that we could go about solving this. But the way that I'm going to approach this is our reactor needs cooling. So this exchanger is going to be taking heat out of the reactor. So I can probably solve for QC if I know the product, if I know the heat of reaction, and I really do a good energy balance on my reactor, I can get QC. So that's what I'm going to go after. Next, I need to set some parameters here, like what's the pressure going to be? What's the temperature going to be? Okay, all those things will be set by what I want to get to the reactor temperature to. And let's say that I wanted to get the reactor temperature to, say, in our case, we want it at 40 degrees Fahrenheit. Okay, so if I constrain this temperature on the cold side to, say, 40 degrees Fahrenheit, how do I find the pressure? Because it's at saturation. Remember I told you the last video that if you know temperature, if you know one of these states, you know the rest of them. So I'm trying to lead you to the other piece of information that I haven't told you. And that is, what type of refrigerant is in the cycle? We need to know that as well. So a couple of things. I'm just going to write them out here. So first thing we have established, we're going to try to solve for QC. The second thing that we've already established is that we need to know the refrigerant. Now I'm going to give you the refrigerant to be R134A, the same refrigerant we discussed in the other videos. And I told you that it's commonly used in the automobile industry. And the reason I'm going to show you this one is because we're going to have a practical exercise where we look at a compressor in my car. And I just want to keep everything constant so there's not too many different variables as you're trying to learn this. But realize in an industrial setting, you're not likely to use R134A. Okay? Now there's going to be some other things that we're probably going to have to constrain. Maybe some more assumptions we're going to have to make. But we're going to walk through those as we get to them, okay? Let's go ahead and let's solve for QC. And we'll come back, fill in QC, get some of our known refrigerant properties, and see if we can start to begin to navigate a way where we can solve for the work of the compressor. Thank you.